Welcome to our final foray into AC circuits. We're going to be examining power-related considerations, and we're also going to make the potential mistake of discussing some of these in a real-world context, actual applications of stuff in Physics 150. I know, I'm sure you're excited to hear this. Keep in mind we are looking at a capacitor, a resistor, and an inductor in series with an alternating current voltage source. The resistor dissipates energy away from the circuit. The resistor is the load. The resistor is the appliance that you've plugged into the outlet or whatever you're using to charge up a device or whatever. The voltage source is the electric company's power, and then electrical engineers have designed electric circuits with capacitors and inductors in such a way as to maximize the amount of energy going to the resistor. Nevertheless, there's always going to be a little bit of energy that just doesn't get used up by the resistor. And there's going to be a little bit of energy that's always going to be in the capacitor and the inductor. And they're going to be kind of alternating from one to the other. The energy in the capacitor is maximum when the charge on the plates is maximum, and that means that charge in the circuit is not moving. The energy in the inductor is greatest when the current is moving rapidly. So the maximum energies occur at different times in the capacitor and in the inductor. How do we calculate the rate at which energy is dissipated? And by the way, that is what power is, the rate at which energy is changing. From our discussion in electric circuits in the DC situation, direct current situation, we came up with the formula that the power dissipated is equal to current times voltage. And that idea is still true. We can talk about the average power dissipated by whatever circuit element we have. So that's what I mean by object. The average power dissipated by the resistor, the average power for the inductor, the average power for the capacitor, the average power for the voltage source. All of that is equal to the root mean square current times the root mean square voltage across that object. So this is where the root mean square values really shine, and that's why root mean square values have some utility in discussions in AC circuits. So just from that, we can say that the root mean square voltage across the resistor is the root mean square current times the resistance. The root mean square voltage across the capacitor is equal to the root mean square the current times the capacitive reactance. The root mean square voltage across the inductor is equal to the root mean square current times the inductive reactance. So that's how we can get the root mean square voltage for whatever the object in question is. If we talk about the power dissipated by the resistor, and as I've said, that's the load, that's the object into which we are feeding the electrical power. The root mean square voltage across the resistor is, of course, equal to the root mean square current times the resistance, but the root mean square current is equal to the root mean square voltage supplied by the source divided by the impedance. If we take these ideas and combine them together, so we have that the average power across the resistor is equal to the root mean square current times the root mean square voltage across the resistor. Well, okay. But we can also say that the average power dissipated by the resistor is equal to the root mean square current times the root mean square voltage of the source divided by the impedance times R. Now, how can I say that? Because one of the formulas we have for power dissipated by a resistor is I squared R. Well, what I'm doing is I'm just breaking that I squared up into two different terms. One of them is going to remain I, but the other factor of I I'm going to call root mean square voltage of the source divided by the impedance. And there's method to my madness. because it leads us to this final equation on the screen, that the average power dissipated by the resistor is equal to the root mean square current times the root mean square voltage of the source times resistance divided by impedance. And so we've related the average power of the resistor to what is being supplied by the source, as well as dealing with the impedance of the circuit. And I want to deal with that expression R over Z. Recall that we treat the voltage across the capacitor, the voltage across the resistor, and the voltage across the inductor as lying along, respectively, the negative y-axis, the positive x-axis, and the positive y-axis. This was how we generated our formula for the impedance, equaling the square root of XL minus XC squared plus R squared. We used the Pythagorean theorem for that. Well, let's take a look at the triangle upon which this Pythagorean theorem of usage is based. One side is R, the resistance. The other side is the difference in the reactances, XL minus XC. And the hypotenuse is the impedance Z. Well, so katoa. Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. I have R over Z in the formula on the previous slide. R is adjacent, Z is hypotenuse, adjacent over hypotenuse is cosine. So I get this term cosine phi, cosine of the phase shift. The phase shift between the voltage source and the current in the circuit, equaling R over Z. And so I can revise the power that is dissipated by the resistor as equaling the root mean square current in the circuit times the root mean square of the voltage source times this factor cosine phi. Cosine phi is a unitless quantity, and it will be between 0 and 1. And in this expression, cosine phi is called the power factor. What we want in an electric circuit is we want our incoming voltage, ERMS, directly sent over to the resistor, the load, which is where we apply the electrical power. We want to transfer as much of that as possible. What we want is the power factor to be as close as possible to 1. If the power factor is 0, then no energy is getting radiated away by the resistor. You might as well not have the device plugged in. But for maximum efficiency, we want cosine phi, the power factor, to be equal to 1. In a purely resistive circuit, that's what we get. If there's no capacitance and if there's no inductance, then phi, the phase shift, will be equal to 0. The power factor is 1. Everything is great. Unfortunately, it's impossible to have a purely resistive circuit. A closed loop of wire, for instance, is going to have some inductance. It's unavoidable. So it's only a theoretical limitation to say that it's a purely resistive circuit. We can get extremely close to it, but we can't get it exactly. At the other extreme, we could have a circuit that is purely inductive or purely capacitive, or just one, or a combination of the two. In that circumstance, the phase shift is either positive pi over 2 or negative pi over 2, and the power factor is 0, and there would be no energy dissipated away from the circuit. This is also a theoretical extreme because it basically says that there's no resistance, and all wires have a little bit of resistance. So we might make the resistance very small, but we're never going to make it identically 0. But these represent extremes. Let's apply some numbers. What is the average rate of energy change? So in other words, what is the power in each circuit element? So in other words, we have to do it for the resistor and the capacitor and the inductor and the voltage source. Oof, we got to do it for four things. We have a 38.1 ohm resistor, a 93.2 microcoulomb capacitor, and a 200 millihenry inductor. The voltage source has a 75 ohm root mean square value, and the frequency is 45 hertz. We also want to find the power factor. No matter what we do, we are going to want to know the angular frequency, which is 2 pi f. So 2 pi times 45 is 282.7 radians per second. The capacitive reactance, 1 over omega c. Of course, the capacitance we have to convert to standard units, so you see 93.2 times 10 to the negative 6. And our capacitive reactance is 37.9 ohms. Our inductive reactance, omega times L, 282.7 times 0.2 henries, 56.5 ohms. The impedance, XL minus XC squared plus R squared. Find that sum, take the square root, and we get that the impedance is 42.4 ohms. Since it's larger than the value of the resistance, I feel pretty confident that this is a correctly calculated value. We want to know the root mean square current. It's equal to the root mean square voltage divided by the impedance we just calculated. 75 divided by 42.4, the root mean square current is 1.77 amps. So now we can calculate the voltages, the RMS voltages across each of the circuit elements. The RMS voltage across the resistor is RMS current times R, 1.77 times 38.1 equals 67.4 volts. The root mean square voltage across the capacitor is equal to the root mean square current times the capacitive reactance, 1.77 times 37.9 equals 67.1. And the root mean square voltage across the inductor is equal to the root mean square current times the inductive reactance, 1.77 times 56.5 equals 100 volts. Interestingly, the root mean square voltage across the inductor is larger than the root mean square voltage supplied to the circuit. This is not violating the laws of physics. Remember that the voltage across the capacitor and the voltage across the inductor will always be opposing each other. So we're safe in this regard. Now let's determine the powers. And each of those powers can be calculated as the root mean square current, which is the same for all of them because they are in series, times the root mean square voltage for each of them. So for the resistor, the average power is 1.77 times 67.4 equals 119 watts. For the capacitor, 1.77 times 67.1 equals 118.7 watts. For the inductor, 1.77 times 100 equals 177 watts. So, what is the average rate of energy change in each circuit element? What is the power in each circuit element? We've done that part. Now, we also have to do the power factor. R is 38.1, Z is 42.4. We get 0.899. Now, the power of the voltage source is going to be equal to IRMS times ERMS times the power factor. The idea of the power factor complicates the situation of a real transformer. Up to this point, we said that in a transformer, the incoming power equals the outgoing power. But to be honest, there's going to be a little bit of that energy lost in the transformer because we have these big old inductors that are trying to diminish the amount of energy that's getting dissipated through resistance, that's getting sent to the other coil effectively in the transformer. Because of non-ideal effects. The power factor is not necessarily exactly equal to 1. Electrical engineers take it upon themselves to try and design transformers that get this power factor as close to 1 as possible. But it's not ever going to be exactly 1. They can pile on the decimal points, 0.9999. They're never going to get exactly 1, but they get awfully close. In reality, it's not that power out equals power in, because some of the power going in is lost. A more accurate representation is that the power in times the power factor equals the power out. The power out will always be just a little bit less than power in, even under the best of circumstances. So we see it a real application in real transformers. We have to worry about those things. That's why electrical engineers make all this money trying to incorporate the right circuit design in order to maximize the power factor. There's always going to be an inductance inside a transformer, but if you can set up capacitors in just the right way, you might be able to achieve resonance. And at resonance with the effects of the capacitor canceling out the effects of the inductor, you can maximize the energy that is getting transferred from one to the other. Another place where this becomes useful is in, well, basically radio. Radio is based on this idea of the inductor and the capacitor in these AC circuits, and also an adapter. Many devices that you're using right now are plugged into an outlet via an adapter. What does the adapter do? Why is it there? This is a real-world situation involving AC circuits. Now, the tunable radio relies on the fact that even right now you are surrounded by electric and magnetic field oscillations. These are called radio waves, as we'll see a little bit later this semester, but they are all around you. And if you could have a device that is sensitive, it could, for instance, detect a changing magnetic field, and that changing magnetic field can induce a voltage, and that voltage means that there's a current, and you can get some interesting effects coming out of it that way. You need to maximize that by tuning your frequency to match the desired frequency you want to observe. How do you tune it? You can play around with the value of the inductance. You can play around with the value of the capacitance until you reach that resonant frequency. If you can adjust the inductor or the capacitor to get to that resonant frequency, you're going to maximize your ability to detect electric and magnetic field oscillations at that frequency. And in a way, that is what radio is. The tuning knob, for instance, can adjust the value of the inductor, and that can then allow you to focus in on a very particular frequency. The actual coil inside there is surrounded by a copper cylinder. The copper cylinder kind of causes stray electric fields to have no effect on the copper coil within, the inductor within that copper cylinder. I don't expect you to follow all of the details for this circuit diagram for an amateur radio, but I want to point out that there are inductors and capacitors in place in this circuit. And you can see a capacitor with an arrow through it indicating that it is a tunable capacitor. So you can tune the capacitor, get it the resonant frequency to just the right value, and pick up a signal that is broadcasting at that frequency. The other real-world application is the adapter. An adapter is that big black thing that's somewhere along your power cord. Maybe it's plugged directly into the wall. Maybe there's a regular power cord that connects into kind of a brick, as they call it, before then extending to your electric device. The adapter takes in AC current and it spits out a very close approximation to DC current. So it allows us to use AC sources by creating a DC situation. How do they do it? Well, there's an important device that's involved called a diode. A diode is another circuit element. It's just one that we haven't discussed before. It has an interesting property in that it allows current to flow through it in one direction with very low resistance, but if you try and push current through it in the opposite direction, it develops very high resistance and prevents that current from coming through. Now, why is this diode important? Because we want to have an output current that is always positive. That's what DC is. If I have incoming current that is alternating from positive to negative, that's not going to be very helpful. What we do is we have a diode that accepts current traveling in one direction, allows that current to travel through it. And then we have a second diode that's more or less identical to the first, but it's wired up in exactly the other direction. So the first diode will spit out half the current. The second diode will spit out the other half of the current. And so what we get with these two diodes, the output, yes, the current is always trying to alternate, but it is only varying from 0 to a positive value to 0 to a positive value to 0 to a positive value. So all of a sudden now we have a current that is always greater than or equal to 0. How do we go from this to a DC current, which would be a flat horizontal line, non-zero but still flat? Well, we actually use an RC circuit. The current enters the RC circuit and it's going to start to decay. Thanks to our understanding of RC circuits, I hope that makes sense. But then this output is starting to decay a little bit, but then in comes the next hump of current, and it brings it back up to the peak, and it starts to decay a little bit. But then in comes the next hump of current, it brings it back up to a peak, and it starts to decay a little bit, and then in comes the next hump of current, and so on and so forth. You might get an output current that looks like what you see on the screen, where it starts at a maximum, it decays a little bit, but gets pumped back up to the maximum, decays a little bit, pumps back up, decays a little bit. This isn't a straight line, but neither is this representative of the actual numbers that are involved in this process, the actual values of the resistance and capacitance. Those are adjusted in such a way that you don't get these bumps, that you get what is, to a very good approximation, a straight horizontal line that appears to all the world like it's DC current. Okay, that's it. Next time we'll start on a new topic. We are done with AC circuits.